So our next speaker is Maye. Maye is a senior engineer of the Institute of High Energy Physics in Beijing in China. She is the L3 manager of the Daya Bay Reactor Neutrino Experiment and Jianmen Underground Neutrino Observatory, so JUNO, experiment at the Guangdong province and a member of the IEEE. She serves as a liaison between experimentalists and computing scientists collaborating on neutrino physics experiments.
And good afternoon. I'd like to introduce the upgrade of the framework of the detector control system for JUNO. First, I will give a brief background introduction, and then I will introduce the requirement, the framework schema, the key technology, and the realization, and then at last I will give the milestone. This picture shows the Daya Bay Reactor neutrino experiment, which located in Shenzhen City in China, and since the Daya Bay experiment layout is electron antineutrino, produced to option antineutrino in a nuclear actor. We position the antineutrino into the it's a little bit smaller of the text show, and the main property of the experiment is to produce the reactor antineutrino, focusing in the near and far side location. And this is a picture of the DCS of Daya Bay. Since most of the system are developed separately by the system, and it has four of the system, which is the AD detector, the muon detector, and the equipment DAQ, and the environment and the remote control. For neutrino experiment, which here is a Daya Bay neutrino experiment, and here is a new JUNO DCS JUNO experiment, which is located in Kaiping country, Jianmen City. The framework of the detector control system, which is showed here, since we have 12,000 channel high voltage channels and 80 front-end electronics grids, and also we have 40 electronics power, and with gas monitoring and PLC, and about 1,000 temperature and humidity sensors, and also we have an interlock and the lead sensor monitoring and the embedded control and the environment monitoring, and we use interfaces with the IPCs with RC 485 and RC232, and also we have CAN bus, I/O, and TCP/IP, and also we're sharing data with the network, and which we build a data sharing pool, and also we can sharing data with the DB server and web remote control server with offline analysis and a data DAQ system, and with the physics users. And for requirement collection of the detector control system, for monitoring and run control, we have the high voltage electronics environment of experiment hall, and the control device like collaboration, gas system, water system, and power supply, etc. And for functions, we have front-end sensor digitalization and data acquisition with GUIs for monitoring and control, and database recording, and the logic for alarm, errors, events, interlock to keep safe, and the embedded remote control modules, and the interface to DAQ and offline software. For system schema, we have a monitoring and run control with high voltage electronics calibration, gas, water system, and the power supply, as well as the environment of the experiment, etc. For for the center of the system is the data pool with DQ with MySQL, and we're sharing data with subsystem with LCs using archival engines, and also with data acquisition program to this central data pool. And we can develop several client GUIs with CSS-based APIs and LabVIEW or the PHP. For data acquisition, we have two ways of getting data. One is using PyEpics through the channel access, and another is archival application. For data acquisition interface, we use this CAGA and JC access with IPEX and ICALEPCS, which is connected with LabVIEW and WebCA. For the pink way is here with PyEpics, and for the blue way is we use a DC web application as well as archival weaver to use with binary data files and archival engine, which based on the IPEX IOCs. And for real-time data transmission and the data format, the real-time data transmission, we use the AJAX, and the windows of AJAX, we use client server and web server based. For data format, we use JSON, and here is a show of the XML-based JSON file, and also we also with the AJAX component with JavaScript with kernel of the AJAX, and XML HTTP request, which can fetch and send data asynchronously. And also we use PHP, which obtain the request from the JS client. For database design, and here is a database structure. We have three kinds of tables with configuration table, alarm table, and data table, which shows here with different colors. And for uniform of the experiment, we provide a naming convention, which provide a variable name of the software integration, the table names, and the word format. Also, we use abbreviations, PV name format, and the output signals. And we also use a DEAM named when sharing data, which provided by Sun, and we share variable named using LabVIEW. And here is the rules of all the naming conventions. For PV name format, we use this kind of format, and for a system, subsystem, and subsystem, we use such as the abbreviation of these detectors and detector and equipment. And for device and device name and numbers, for example, for NEM crate, we use their numbers of the NEM crate. And for device specification part, we use this kind of LCs we can provide it, and the output signal is generally set at the end. Beyond that, we since the JUNO is under construction, we settle a JUNO prototype, which we have built a DCS in the prototype. From now on, we have crates and servers. We have these numbers of crates for PMTs and high voltage, and the NEM crates for NEM, and winner crates of front-end electronics, and with 4 temperature sensors, and also with temperature, humidity, and pressure sensors. And we also have 2 servers of IOC firmware and the database, and with 2 temperature, humidity embedded servers, and with 1 IPC for GUIs. And here is the prototype of the server and the network. At the base, we have a storage server. Upon that, we have a EPIX CSS archival engine host, and we use a ICN switch with gigabits fiber with high abilities of servers with 10 gigabits Ethernet to the IOCs of the subsystems. We have 4 servers with 3850 and 3650, and we also have 10 gigabytes storage and 4 IPs and 6 IPCs. And we also have several ways of remote monitoring, which one is for archival-based development, which function is to real-time data and real-time chart, and also with historical chart. And also we plot PV chart on the archival viewer with client application. Here we go see Milestone. The project is start from 2013. We collect the requirement and investment, and now we go to the 27 this year. We go function realization, interface defined with subsystem, and test bed maintenance, also with sensor installation of liquid scintillator filling. Also we have IOC study of all the embedded system, and also we do the R&D of the embedded system of the temperature and the humidity, and we also archive and the database demos, and also we do the remote monitoring R&D. Thank you very much.
I think you have multiple places distant several kilometers. So do you have 2 DCS systems in the future?
VC system?
You have 2 neutrino detectors, I think.
Yes.
So DCS systems, will you have 2 different DCS systems?
No, the new system is upgraded from the old system. The old system is developed by a Daya neutrino experiment, but it's based on the LabVIEW. Most of the software is based on the LabVIEW and the PLCs. So we have, I want to uniform with this system with ICALEPCS system, and because the LabVIEW and the PLC system is restricted by the operation system and the upgrade of the LabVIEW commercial software platform.
So I have a quick question. How long had you been running that experiment prior to the 2013 upgrade?
How long?
How many years was the system running before you started doing the upgrade?
The database system of the DCS, the system running start from 2012, and it's from now on it's have 5 years running.